Hi everyone, my name is Özgür Çapınoman. I'm a PhD candidate at Penn State University, and I'll present our work on behalf of our team and collaborators at Format Lab, led by Benay Gürsoy. Unfortunately, due to some complications, we couldn't be there to join the robot community in person, but we're excited to present our collaborative work on conformal robotic 3D printing and post-fabrication analysis of mycelium-based composites. This work has been a culmination of various lines of ongoing research at Format Lab, including my PhD research on vision-based sensing and digital twin reconstruction for adaptive robotic fabrication workflows, my colleague Alale Mohseni's ongoing research on developing recipes and workflows for robotic 3D printing of mycelium-based composites, and a former member of our lab, Natalie Walters' research on acoustical properties of mycelium-based composites. Together with our collaborator Alireza Zamani, and our advisor Benay Gürsoy, our research presents an exploration into advanced slicing techniques and vision-based sensing frameworks for precise material deposition and post-fabrication monitoring of mycelium-based composites. At Format Lab, we explore the relationship between form and matter, fabrication and performance, mediated through computational design paradigms and emerging digital technologies. Over the years, our lab has engaged in a broad spectrum of projects involving various fabrication techniques and material systems. Currently, our lab's primary research areas are focused on adaptive robotic fabrication, as well as biomaterials and advanced biofabrication workflows. Through this research on biomaterials and advanced biofabrication, our goal is to propose sustainable alternatives to contemporary construction practices and encourage a shift towards a circular economy in which waste is considered a resource. Currently, the building and construction industry is responsible for 39% of global energy-related CO2 emissions. The traditional life cycle of building materials, from extraction and manufacturing to transportation and installation, consumes substantial energy and typically follows an unsustainable produce, use, discard model. In response, we envision a circular built environment in which building materials can be grown locally and discarded sustainably at the end of their life cycle. Today, we're excited to showcase the most recent outcome of this line of research, exploring a robotic additive manufacturing method that integrates hybrid slicing and conformal 3D printing to fabricate geometrically complex acoustic panels using mycelium-based composites. Although this geometric complexity is a key factor in determining acoustic performance, fabrication of such complex panel geometries poses significant challenges to traditional slicing methodologies. Moreover, mycelium-based composites are known to shrink and deform as they lose moisture, which further complicates achieving the desired level of geometric fidelity. To document and quantify these geometric deformations, we employed a vision-based sensing framework to reconstruct digital twins at specific stages of cultivation, aiming to better understand the material dynamics at play. In our presentation, we will discuss both the process and the results of our hybrid slicing and conformal 3D printing efforts, along with the findings from our analysis of post-fabrication deformations. Before I explain our methodology in more detail, however, I would like to briefly introduce mycelium and mycelium-based composites. Mycelium is the vegetative root part of fungi, which is a part that we typically do not see in mushrooms. In simpler terms, mushrooms are the fruiting bodies, and mycelium is the root system. And mycelium-based composites are biomaterials derived from colonization of agricultural plant-based residues by mycelium, typically by ceasing the colonization process at a controlled stage before fruiting bodies emerge. Recently, this material system has garnered significant attention as a novel approach to repurposing waste streams into valuable resources. Instead of intensive material extraction and processing, mycelium-based composites present a cost-effective and biodegradable alternative. Moreover, recent studies demonstrate promising material properties of mycelium-based composites, presenting compelling alternatives to petrochemical, synthetic, or cement-based architectural materials. Here you can see various projects showcasing the use of mycelium-based composites in architecture, including some of the previous work from our lab by Gazvinyan et al. And Walter and Gürsoy. However, the prominent method of fabrication in these examples heavily relies on molding techniques, which is often wasteful. In response, 3D printing of mycelium-based composites presents a promising alternative to reduce mold waste and enables the fabrication of more complex shapes. Here you can see the pulpefaction project on the left, featuring a column made by growing fungi using fiber byproducts, printed in separate parts, and then assembled. The tree column, standing 2 meters high, was similarly fabricated in 10 separate modules. And the mycoclay collection on the right combines 3D printed fungal mycelium with earthenware clay and industrial waste. However, adopting 3D printing for mycelium-based composites is not a straightforward task. As you can observe in the pulpefaction and tree column examples, mycelium-based composites often exhibit substantial deformation due to water loss, resulting in significant shrinkage and deformation. Due to the material's anisotropic nature, notable deviations between subsequent sections significantly complicate such multi-part assemblies. Moreover, current applications are primarily limited to planar slicing approaches, which further impact the geometric fidelity due to the stair-stepping phenomenon. In our research, we present an integrated approach to robotic additive manufacturing of mycelium-based composites through 3 targeted interventions at the design, prefabrication, and analysis stages, as highlighted here. In our exploration, we define an experimental design space using an interference pattern synthesized from a 2D simplex noise and a 1D sine wave, which enabled a high degree of control over tuning geometric feature frequency. This wall section was divided into 96 unique panels, each measuring 25 by 25 centimeters. For our fabrication experiment, we chose one of these panels characterized by its high-frequency features, which presented a challenging case for traditional planar slicing. Similarly, non-planar slicing of this panel was impractical due to the extreme variations in layer heights. To address these issues, we adopted a hybrid slicing strategy. This approach merges the computational efficiency of planar slicing with the geometric accuracy of non-planar top layer deposition. To achieve this, our additive manufacturing strategy employs 3 core computational approaches. In the geometric discretization step, the print volume was divided into 2 volumes based on the desired total number of conformal layers. These print volumes are then used in toolpath generation stage. In both planar and non-planar toolpath generation tasks, we employed differential growth curves to ensure geodesic dispersion of laid material filament, enabling us to controllably vary deposition density. Due to the differential growth curve's intrinsic nature as a surface filling curve, the resulting toolpath inherently conformed to the layer boundaries. Moreover, this resulted in a single continuous toolpath which minimized disturbances due to the travel between distinct print islands. Lastly, we adopted a simple pose optimization approach to avoid collisions and maintain the fluidity of deposition in non-planar layers. Using a weighted average between the surface normal vector at each robot target and the world z vector, we were able to correct extruder poses. These toolpaths were executed using the ABB IRB 2400 industrial robotic arm, coupled with a custom-fit WASP extruder end-of-arm tool and 5-liter pressurized material tank. This robotic work cell setup was critical in working with mycelium-based composites to mitigate contamination, as these parts allow for easy disassembly for sterilization. Moreover, the pressurized material tank provided a secure and airtight container for transporting living mycelium mixtures from sterile lab environments directly to our robotic work cell. In our fabrication experiments, we made use of Ecovative's pre-inoculated, dehydrated grow-it-yourself mushroom bags. In order to develop an extrudable paste with this pre-inoculated dehydrated material, its particles were ground down to a finer size and sieved. The ground material was then mixed with sterilized water, flour, and a gelling agent to achieve an extrudable mixture. Here you can see a quick time-lapse of the 3D printing process. Starting with the planar layers, we observed consistent laid material width and no significant over or under extrusion of material. Similar results were also achieved in conformal 3D printing of non-planar layers, where the material deposition closely conformed to the top surface geometry. Following the fabrication process, we were able to achieve successful colonization of the printed substrate as presented in this slide. During this post-fabrication stage, we employed a vision-based sensing framework to digitally capture and reconstruct panel geometries at different stages. Here, we used Microsoft Azure Connect Developer Kit along with a Jetson Nano Edge device to synchronize data acquisition at precise camera poses sampled from a hemispherical trajectory. Using this outside-in trajectory, we were able to sample the printed panel from different perspectives, aiming to fill in potential missing data due to occlusions. These reconstructed geometries were then compared against both the digital model and each other to determine the difference in geometry between stages. Using a sign distance approach, we were able to quantify these changes using descriptive statistics. The materialization error captured by the comparison between the AB pair presented significant overextrusion along the valleys. We believe this is primarily caused by the material spring back, where we observed the extruded material to expand slightly after deposition. Similarly, we observed a loss of geometric fidelity around the edges, likely due to the limitations of large-scale 3D printing. As illustrated by the comparison of the BC pair, the change during the growth phase was minimal and uniform. Here, both the mean and standard deviation values were the lowest among all other stages we analyzed. During the air drying stage, however, we observed a reversal of this uniform shrinkage behavior. The comparison between the CD pairs illustrates the spatial distribution of these changes, signifying localized changes around the corners of the panel. The oven drying stage followed a similar trend and presented the highest rate of shrinkage, with nearly 10% volume loss from the air drying stage. And cumulatively, we observed a total of nearly 18% of volume loss and observed significant deviations around the corners due to uneven loss of water content. Overall, our study presented an improved material deposition strategy for mycelium-based composites, harnessing novel slicing strategies to improve geometric fidelity. Furthermore, our examination of vision-based sensing paradigms for post-fabrication monitoring of mycelium-based composites marks preliminary investigation into understanding and controlling post-fabrication deformations. Going forward, we're interested in pursuing this exploration, investigating the effects of various fabrication parameters such as infill pattern and density to fine-tune material properties, including acoustic absorption. Moreover, we believe that the collected monitoring data can be used for modeling material behavior using generative machine learning models to account for adverse effects of post-fabrication deformation. This concludes my presentation. If you have any questions, please feel free to reach out to us. Thank you.